Okay, so today we're going to look at two-dimensional motion, problem A. And that reads, a swimmer runs horizontally off of a diving board with a speed of 2.5 meters per second and hits the water a horizontal distance of 1.9 meters from the end of the diving board. How high above the water was the diving board? All right, so we still follow that same process as we've done for all our kinematics motion. First, identifying the object we care about the motion for, and that is the swimmer. All right, then we want to define what begins that motion and what ends that motion. Again, I'd encourage you to do everything by pausing the video, checking your work, that sort of game. All right, so what defines the motion? Well, when they leave the diving board. That's when we start to care. And when do we stop caring? Well, when they hit the water. So we start caring when they leave the diving board. We stop caring when they hit the water. Now we want to ask ourselves, is this one dimension or two dimension? Well, they're running across. They're kind of traveling both horizontally and they're falling, so two dimensions. So we're in two-dimensional projectile motion. Are we in a state of free fall? Yeah. Once we leave the diving board, it's only gravity acting on the swimmer, and so we're in two-dimensional free fall. Okay, now we have to define the world. Draw our picture, set our origins. And I made that plural. We have to be thinking about two. So here's our swimmer, the end of a diving board. Here's the water below. We need to define both the vertical origin and the horizontal origin. And so horizontally, that's dividing the worlds into lefts and rights. Let's set our horizontal origin at the end of the diving board. Vertically, that defines our world up and down. We'll set our vertical origin at the start of the swimmer, where the swimmer is going off the diving board. So horizontally, dividing the worlds in lefts and rights, we're at the edge of the diving board. Vertically, defining the worlds up and down, we're at the location of the diving board. Okay, now we have to make our list. Two dimensions, two lists. So we have X initial horizontal, X final horizontal, our initial velocity, so initial and final positions in the horizontal direction, our initial and final velocities in the horizontal direction, our acceleration in the horizontal direction, and our time. We don't need that horizontal on there because the time is the same whether we're moving in one dimension or two dimensions. Both have to have the same time. So this is our horizontal motion, and we also want a list for our vertical motion. So we have initial and final positions vertically. We have initial and final velocities vertically. We have our vertical acceleration, and we have our time. So those are our two standard lists. I encourage you to pause the video, fill those lists in, and then restart and see if you match. All right, our initial horizontal position. Well, we've defined that edge of the diving board, that leaving the diving board position is our horizontal 0. So that's going to be 0 meters. Our final horizontal position, we're told the swimmer lands 1.96 meters away from the edge of the diving board. So our ending position when he hits the water must be at 1.96 meters. Initial velocity in the horizontal direction. We're told that the swimmer runs off horizontally, purely horizontally. So he has horizontal motion when he leaves that diving board. And we're told it is 2.5 meters per second. Now, the way I've drawn this picture, he is running in the rightward direction. So this velocity should be positive. Same with my position as I've defined it. Final horizontal velocity. Well, I want to remind you that when we're dealing with two-dimensional motion, free fall, gravity is the only thing acting. And gravity, of course, only acts in the vertical direction. So we know there's no change in the motion horizontally. Our acceleration is 0 meters per second squared. If there's no change in the horizontal motion, the final velocity has to equal the initial velocity. So again, since there's no change horizontally, since in two-dimensional free fall, projectile motion, our acceleration horizontally is 0, the initial and final velocity must be equal. There's been no change. All right, and we don't know our time. Not given in the problem. All right, what about that vertical direction? Well, where does the object, the swimmer, start? What is the position when he leaves the diving board? We've defined that position in the vertical dimension as 0 as well. Where does he land? Well, the problem doesn't say how high the diving board is. It doesn't tell us what that water level is vertically, so we don't know. Initial velocity vertical. The problem says he runs purely horizontally. So it's as if he is dropped in the vertical dimension. There's no initial vertical motion. So that is at 0 meters per second. Final vertical velocity? We don't know. It's not given in the problem. Acceleration in the vertical direction. Well, we've defined the problem as being in free fall. That's the object is only under the influence of gravity once we start carrying, once he starts leaving the diving board. And so our vertical acceleration is that which is due to gravity, negative 9.8 meters per second squared. And just like with the horizontal direction, we don't have any idea what the time is. Those two have to be the same. Okay, so what answers our question? We're interested in knowing how high is the diving board. Well, that is vertical information. Height is related to the vertical. So we want to know that final vertical position to get a sense of our height. And if we're looking at position, we're going to use that position equation. All right, so x final in the vertical direction. We don't know what it is. It stays its variable. We're using this vertical list. Remind ourselves up there. X initial, well, that's 0. V initial, it's 0. We don't know the time. That remains a t. Plus 1/2 negative 9.8 t, again, squared. So I simplify this equation. I get x final equals negative 4.9 t squared. Two unknowns. I can't solve it. I need time. Time becomes a variable of interest. So now I'm interested in getting my time. Well, the verticalist isn't going to help me. If I use my other equation that has time, I don't have V final. So that's not going to work. So I need to utilize horizontal information. It's the same time, so we can use the horizontal motion to help give us some insights. What equation do I use? Well, V final is the same as V initial, so that's not going to help me. Let's look at our position. X final, again, is x initial plus V initial times time plus 1/2 acceleration times time squared. X final is 1.96. X initial, well, that was 0 at the start of the diving board, plus V initial, 2.5 times my time t, which is unknown, plus 1/2 acceleration of 0 times my time squared. So this is using our horizontal information to go after time. Well, 0 times anything is just 0. I can get rid of that term. And I'm left with my time of equaling 0.784 seconds after I do my algebra. Okay, so now I have that time. And I can use it to finish up my problem. So x final, we still want to know what that is. We don't know. X final in the vertical direction is equal to negative 4.9 times, now I have that calculated time, 0.784 squared. And I can solve for x final. X final is equal to negative 3.01 meters. Now, we have to see if that makes sense. Does the negative make sense? Well, I set my origin at the top. I better have a negative position below the origin, so that does make sense. And if we're going to define the height, we can say that the height is 3.01 or a 3-meter diving board. So our position is appropriate And of course, then our height implies the 3-meter board. All right, two-dimensional motion, twice the amount of work, but recognizing some of those connections. Same process, identifying what we care about, identifying that motion, defining our world, but making sure we have set two origins, an origin that defines up and down, an origin that defines right and left. Once those motions are independently thought about, we can do that motion independent, our horizontal list independent of our vertical list. We still go after what we want. We want to know the height, and the height is vertical information. So we go after that vertical position, recognizing that we need time, but appreciating that time is also related to horizontal motion. And so we can use the horizontal motion to define the time, use that time to define our height, and solve our problem. All right, good job.